Hey guys, and welcome to part 2 of the relative strength of acids and bases series. And in this video we are going to talk about how to decide the strength of bases when the atom carrying the charge is same. In part 1 of this video we have discussed that if we have something like NH2 minus and OH minus where the negative charge is on different atoms, then how to predict the basicity. And now we know that NH2 minus is more basic than OH minus. But what if the atom carrying the negative charge is same? For example, CH3 C double bond O minus has a negative charge on oxygen, and CH3 CH2 O minus also has a negative charge on oxygen. So how to decide which is more basic in such cases? We can't do this by looking at the atom carrying the charge, so we take help of the second factor, and that is resonance. Before I proceed, sorry about my sore voice today. I have caught cold, but that's not going to stop me from making this video. I hope that it's not too uncomfortable listening to my sore voice. But anyway, let's proceed. So the second factor is resonance, and it helps us decide the strength of acids and bases. Let's see how. For that we will take two examples. We have CH3 C double bond O minus and CH3 CH2 O minus. Now in each of these examples you can see that the negative charge is present on the oxygen atom, and so we cannot decide the basicity based on the atom. So what do we do now? Look at the first structure, that is CH3 C double bond O minus, and you will realize that this negative charge present over here on this oxygen atom is in conjugation with this double bond here, and therefore this species can have resonance structures, and we can draw the resonance like this. This negative charge will come over to form a bond, and that will cause this carbon atom to have 5 bonds, and therefore we can break this pi bond and we will get a resonance structure which looks like CH3 C O minus double bond O. So the first species has a resonating structure, but the second species, that is CH3 CH2 O minus, does not have resonance. And what we know is that resonance increases stability, right? Resonance causes an increase in stability. So the first species, that is CH3 C double bond O minus, is more stable than CH3 CH2 O minus. And because of this, the basic strength follows the reverse order, that is CH3 C double bond O minus, it is also known as the acetate ion, is less basic than CH3 CH2 O minus. This is the order of basic strength. So when you can't decide the order on the basis of atoms, then you look at the resonance structures, and the more resonance structures present, the more stable the species will become. So if I take another example with HC double bond O minus and CH3 O minus, then which of them is going to be more basic? You can see that the first structure will have resonance and the second structure will not, and therefore the first structure is more stable than the second structure due to resonance. But when we talk about basic strength, the order will reverse, and so HCO minus will be less basic than CH3O minus. But what if both the structures have resonance? Then we will have to see which species has greater resonance and therefore is more stable. Usually, more number of resonating structures means more stability. There is an exception to that, which we can see right now. If we have a phenoxide ion, which we can draw as a benzene ring attached to an oxygen atom with a negative charge, this is the phenoxide ion, and you can draw the resonance structure for this ion quickly like this. So you can see that this phenoxide ion has 5 resonating structures, and therefore it is going to be very stable, right? So this phenoxide ion is quite less basic, and in comparison to this, if we draw the acetate ion, which is CH3 C double bond O minus, it has only 2 resonating structures, which are so obviously the rule is more resonating structures means more stability, but in the resonance of acetate ions, look at this negative charge carefully. It is going from an oxygen atom to another oxygen atom. Whereas if you look at the phenoxide ion, you will see that the negative charge is going from an oxygen atom to a carbon atom. And because of this reason, the acetate ion has a greater resonance compared to the phenoxide ion. And so, phenoxide ion is less stable than acetate ion. This also means that phenoxide ion is more basic than the acetate ion. So guys, that's how you use the resonance effect to predict the order of acidity and basicity. Now that we have looked at the second factor, let's see where this does not work. What if we have to compare two compounds like CH3 C double bond O minus and Cl CH2 C double bond O minus. Both of them have the negative charge on the oxygen atom, so we cannot use the first factor. Then both of them will have the same amount of resonance, so we cannot use the second factor. Then how do we predict which one of them is more basic? Now comes the third factor, which I will describe in the next video. See you.